Okay, in the next, let us talk about the easier aspect of the error measures. That is to measure the difference between the desired um, target value at a data point and the predicted target at the point by our model or a hypothesis. We recall that the error measure is to measure the difference between two functions. So now we consider how about, so you can of course try to define some kind of measurement of the distance between two different functions in some weird way. But in a large useful family of this definition comes down to the intuitive and natural approach, where we define the difference between the the value of the two functions at one point and average over the all the possible domain of the function and get the error measure. So there are some commonly used point-wise errors. For example, when the task is a regression task, that is, the target value of interest is some real value target, we can use squared error between the desired value and the predicted value at a point. Let us see the target function is f, and the function returned by the function we want to evaluate is some hypothesis hx, and we can use the squared difference between the two functions result at the x as the error. And for a classification problem, this somewhat funny looking symbol represent okay, in the bracket, if the condition we are testing is met, then those one function this testing function returns 1. Note that we use both typeface for this one to represent this is a function, this is not a constant one. So therefore, when the prediction of our hypothesis is not the same as the target class at some x, as the input x, we will count that as one error. Otherwise, we will this is error free when the two classes are same. There are some alternatives in excuse me, each of those tasks. For example, in the regression, you can use absolute value rather than the squared error for the point-wise difference. So basically, there are not too much to consider when the task is clear, and when it comes to simple classification task, and the definition is quite clear. But there are some practical considerations I would like to remark here as side notes. There are some decision costs. For example, considering that you are facing a classification problem, and it is common, as we have said, classification problem takes the incorrect predictions as one error, and that is commonly for all kinds of misclassification. But consider the scenario that you are running a security company, and the classification task is to identify whether the user is, for example, you are measuring the biological features of the user, such as the face, and you want to classify if this face belongs to the face, the identity that has been recorded in the identity card that is presented at the access of the system. So in this case, if you predict positive, then that means the system deems that this is a genuine user and will allow access. And if you predict negative, that means this is an invalid attempt to access the system. So if you have misclassified the, of course, when the ground truth, that means when the user actually is the same user as the identity card shows, that is truly positive and you predicted positive, there is no cost. And of course, when it's truly negative, you don't have any cost either. The cases that are of interest is when the user is not as shown on the identity card, but you have predicted it as positive, then that's a false positive. You mistakenly allows access to somebody who should not have access to the system. And on the other hand, you may mistakenly deny someone who should have access to the system. So in this, by framing the two types of error in the way that we have mentioned, we have already incorporated the business understanding in the measurement of error. You have different costs of making different decisions when the decision turns out to be wrong. In this case, when you made a false positive decision, you may create an important violation of some security policy of the system, which can be very costly. On the other hand, you might create some inconvenience of a genuine user, and all the costs for the user is just to retry, maybe, which is not ideal but acceptable. On the other hand, let us consider another example. For example, you've some automobile service and you want to test the brake system of your customer, and the positive classification means, according to your diagnosis, according to your test examination, the brake system has some potential to failure. You need to fix it. There is some issues with the brake system. On the other hand, if it's negative, then the system is roadworthy, and you can flag a green light for the customer's car In this case, it does not. You can imagine that when it is false positive, that may cost the customer a little bit dollar, or may cost your business a little bit money to retest or do further examination. On the other hand, you may have sent not roadworthy cars on the road and with potential dangers. So in this business understanding, the decision costs are quite different from the previous one. So this is one kind of complexity in considering the seemingly simple determination about measuring the errors. On the other hand, some of the tasks, when the prediction is structured, when the prediction itself has some complexity within that, it might not be so easy to define a simple error, even for an individual data sample. For example, in the object detection based on computer machine vision input, the samples are images, so the data are pixels in the image, and the output of the prediction are the locations and the shape of regions in an image that may contain interested objects. In a traffic scenario, the system is supposed to detect cars, cyclists, the person, so on and so forth. Then when it comes to define specifically the error mirror, you may need to think carefully to assign the value to a box that the system claims it contains a car, but it partially aligns with some objects that does corresponding to cars, but also contains other subjects and contains some irrelevant regions of the in the image. So how to assign a simple real value cost to this single box? That is very very good question, worthy investigation. Another example, there might be machine translation. Say if the input is I ate an apple and I want to translate this English to Greek. So the system may need to determine what is the next Greek word. So sometimes it may need to frame because generally there are multiple correct translations for any single input sentence. Human language are very complex and flexible. So maybe the error mirror needs to take this into account, and considering the previous output words of the system, and actually determines, given the input sentence and given what I had output, then I will assign some cost to the next output. What if I output this word? This could be correct, and if I maybe choose another word, that could be inappropriate in this context. So for summary, is that ideally the error mirror should be based on business understanding. So ideally, the user of the system should provide it. But of course, in practice, actually in most cases, practical cases, the user will not give you a very explicit error mirror. The user may just sit down and discuss with you the business problem, and it's up to you, the data analyzer, the data analyst, to actually get what is the business understanding, and according to the design system, how to design an appropriate error mirror for the business problem. And in many cases, it is not so convenient or possible to define an ideal error mirror completely reflecting the business problem. Imagine the object detection problem. In the real world, objects are occluding each other in each image, and the system, according to different kind of constraints, for example, may only be able to output rectangular detection regions. Then there won't be any ideal definition of what is absolutely accurate mirror of how rectangulars corresponding to all kinds of objects in an image. So then in practical design, it may come to two other principles. First, plausible. Sometimes by some analytic discussion, you may find some error mirrors can have some theoretical value, and we may as well to employ this kind of errors, such as if for many prediction problems, we may think the the target value follows a Gaussian distribution around the correct value, then we can employ the squared error. If you are not very familiar with Gaussian distribution, don't worry. You can check some references and we can discuss this later. And secondly, you may consider the feasibility. Sometimes the error is ideally defined, it makes much sense, but the error mirror's point is to allows us to select the optimal hypothesis in the family. So an error mirror must be mathematically manageable, so much so that we can use it to select members in our hypothesis family. Therefore, mathematical manipulation is also important for the mirrors. For example, in some applications, maybe absolute value error mirror makes more sense than square error. However, absolute value functions is more difficult to optimize than square errors, but it's doable. On the other hand, for classification problems, if you simply counting the error that has been made by a classifier, that could create huge problems for the optimization process. So sometimes we need to find some delegate, some surrogate error mirrors that we hope it can track those ideally defined mirrors, but is more mathematically manipulable.